the ground, you feel it moving with the revolution.
Come on. Hey everybody, it's Obi-Wan Piz for N Simplex Pachinko. We are going to be looking at this paper on integral differential calculus as opposed to differential integral calculus. I think we looked a little bit at this like at some point in the past, but I might have just looked at the abstract, maybe the first couple of pages. But I may have been super tired. Anyway. This is from the 21st of April, 2026, by Grant Molnar. Oh, yeah, this is only through May 12th, so. Oh, right, I've already got the PDF up. Silly. Yeah. Huh. That wasn't what I meant to do, but alright, cool. I was kind of hoping it would give me a just a little quick mention as to what institution he was part of, but it's all good too. Right, so we give an exposition of Newton-Leibniz calculus. We begin by defining the integral as a limit of Riemann sums first. Verify the integrals of the standard catalog of functions by direct manipulation. Prove the substitution lemmas as theorems about Riemann sums. Cross the fundamental theorem of calculus. And harvest the differential calculus on the other side. So things are slightly backwards from the way that most of us would understand it. And so we'll see what Grant Molnar's approach is as we go through it. In this note, we define the integral as a limit of Riemann sums, verify its standard properties, compute integrals using the usual catalog of functions directly from the definition, prove U substitution and integration by parts as theorems about Riemann sums, and then cross the fundamental theorem of calculus and harvest the derivative table on the other side. It's pretty much literally the abstract. Developing the Newton-Leibniz calculus in this way is natural and beautiful. We'll see. Several of the direct integral evaluations, the geometric series arguments for integrals of b of t dt, cosine of t dt from 0 to x, and sine of t dt from 0 to x, and the telescoping argument for integral of secant squared of t dt from 0 to x, and cosecant squared of t dt from a to b, and the equation, functional equation derivation of log from integral of dt over t from 1 to x are instructive in their own right, and the chain rule and product rule fall out from U substitution and integration by parts as pleasant corollaries. Some authors have advocated for an alternative order for an alternative order in which one begins by defining the derivative as a limit of difference quotients, verifies analogous rules, linearity, product rule, chain rule, derives the integral table from the derivative table after crossing the fundamental theorem of calculus. This alternative has some computational advantages. Elementary derivatives are mechanical to compute, and a student following this order requires a great deal of fluency with the formalism before encountering any difficult integration step. However, many students under this pedagogy never develop a firm geometric intuition for integration and lose the direct view of where the integral table comes from. Readers interested in the differential first approach may consult the peculiar references on the subject, among which number 8 is representative. Spivak. Yes, okay. So I have heard a number of people say that. Oh, yep, at Gmail. So not not necessarily with any particular institution. So yeah, Michael Spivak is one of those Publisher Parish Press 2008. Oh no. I didn't know that was a thing. Anyway, yeah, so Spivak's calculus is one of those that comes up often when talking about, like, what calculus book did you ever use? Many of the other ones include... Oh, come on. Stewart. And... I don't remember the one we had. I had Stewart in high school. We had the red book. And I don't think I have it here. I think it'd be crazy for me to bring it. Yeah, no. Not so much. But we taught out of, well, primarily over the last couple of years, over the last like 10 years, we've been teaching out of the OpenStax textbook. Hey! It's Slim! Academy of Useless Ideas and Raiders. Hello, Nimdoc. How are you? We're doing pretty well here. Got some new toys. Gonna have to attempt to figure out if we can get a boom for it, but we have a microphone now. And an XLR at that. We also have a mixer to go with it. So, in theory, over the next month or so, we should actually have, like, no offense to this thing, but we should have slightly better audio equipment. Woohoo! Yeah, I mean, I'm working off of this at the moment, but still, it works. We also had bone conduction headphones, which unfortunately have not been playing nice with Linux, but we'll see how all this works. Hopefully, those at least will be my monitors, and then I'll have the big microphone. See how it goes. Like I said. Yeah, at the moment, I just need something to screw into the bottom so that it can actually sit. And then we'll figure out the best way to hook up all the audio, and it'll be great. Also, tomorrow, I think I'm probably going to be doing a Some Assembly Required stream, because I also got a 108 centimeter by 108 centimeter bookshelf. So I'm hoping that that will go right here, pretty much like next to the door-ish, up to pretty close to where the printer is right behind me. We'll see how that goes. I mean, it'll be easy enough to make. The thing is 34 kilos, so the box was pretty difficult to get up the stairs. My spouse and the older teenager is like, "Do you want help?" I'm like, "No, I'm good." Gonna give myself a hernia, but it's fine. If anyone does not know, Slim from the Academy of Useless Ideas. Please go follow the link. Give him a follow and learn some more math. So, yeah, things are going pretty well here. I didn't stress myself too much trying to get the 34 kilo bookshelf up the stairs. I'm gonna keep mentioning it. Right now we're looking at Grant Molnar's integral differential calculus on arXiv. Kilogram, 2.2 pounds. So, roughly speaking, right, 68 plus 6.8. So, pretty much 75 pounds. But, I mean, once I got it in the house, it was fine. Because then at least I could use the stairs like a ramp. So, I mean, like, the younger one is heavier than that, right? So, I should be able to just, like, haul it right up over my shoulder. We don't do that. So, Molnar's suggestion is to start, rather than with differentials and starting with finding derivatives, but rather work the other way around. Start with the Leibniz calculus, and specifically calculus of integrations. Work on a geometric concept of how this all works, then work our way backwards using slope, because we've been doing slope forever. So, should make it rather interesting. Yeah, a lot of people don't have calculus, or they have a subject-specific calculus. So, I know that a lot of the psych majors at the University of New Hampshire, where I went, took calculus for life sciences. And so it was, you know, psychology, but also life science, like biology and pre-med, that sort of stuff. Okay, conventions and prerequisites. We use the Riemann integral throughout. I actually had a student who came to me one day and was like, "Yeah, one of those guys you mentioned is like one of my ancestors." And I was like, "Excuse me?" She was like, "Yeah, I'm not sure which one it is. I'll ask my mom again." But like I mentioned his name, and she was like, "Oh yeah, we're related to him." So she came back the next day and was like, "Yeah, I think it was like I'm like, Bernhard Riemann?" And she was like, "Yeah, that one." Like, well, that's impressive. She's like, it didn't really pass down too well. Like, That's not how mathematical prowess works, unfortunately, but she did quite well. I was proud of her at the end because she worked hard. The gauge Henstock-Kurzweil integral has well-known advantages for proving the fundamental theorem of calculus in maximum generality, but will only ever integrate continuous functions where the two integrals agree and the Riemann construction is more familiar. We assume the reader is comfortable with the construction of the real numbers and other basic ideas from real analysis, such as completeness continuity, including uniform and Lipschitz continuity, and the intermediate and extreme value theorems on a compact interval. We assume that sine and cosine have been defined geometrically, for instance via arc length on the unit circle, yes please, or as the unique continuous solutions to the addition formulas with appropriate normalizations. That one, I mean, obviously I know what it is, probably, but it's going to take me a minute. Unique continuous solutions to the addition formulas. Ugh. And that the addition and half-angle identities are at our disposal. Okay. We also recall the geometric observation that the limit as theta goes to 0 of sine of theta over theta is equal to 1. No further prerequisites are presumed. That's pretty nice. The integral as primitive. We collect the definition of Riemann integral and a handful of its standard properties. So, a tagged partition of the interval from a to b is a sequence a equals t0, which is less than t1, which is less than t2, etc., up through tn, equals b. So we start from a and go to b, where a is t0 and b is t sub n, together with tags c sub k belonging to the interval from t sub k to t sub k plus 1. Its mesh is max sub k of t sub k plus 1 minus t sub k. Right, we're going to do a visualization of this because that's unfair to anybody who doesn't know what that is, just offhand. All right. Nope, hang on. Where are we? Yeah. Boop. So yeah, go over here, reset the canvas. Oh well. I mean, honestly, that part of the picture could have helped a little. Wait, where did the... Yeah, there we go. Right, so the Riemann integrals, or Riemann sums that they're talking about, are working off of something roughly speaking like this, where we're going to split the interval between a and b into some number of parts. And this one here is pretty particular as far as how I made it work. This is where our delta x, the difference between one and the next x values that we're going to use, are effectively all the same size, delta x. That is effectively, in this case, what we call the mesh. The mesh is just going to be the largest space, the largest delta x that we find in that interval. So one of the things they sometimes do is say, okay, look, we're going to draw out this particular function. We want to know what the area under the curve is from A to B. And it's possible that we could take each of these values and say, like, okay, we're gonna vary the size of each of these rectangles. They're going to be smaller on any of these really steep parts, and they're going to be a bit wider they're going to be a bit wider on like the flatter parts. That way we tend to minimize the error, at least somewhat. And so like this right here is going to be delta x1. This is 2, 3, 4, 5, 6, 7, 8, 9. So this one right here is going to be delta x sub 9, 10, 11, 12, 13, 14. Delta x sub 14. All right, so because those are in those particular places with those particular values, we're going to look back at what the definitions were that we're talking about here. All right, so a tagged partition of A to B. So in this particular case, the partition splits the interval A to B into some number of discrete parts. So again, in this case, the stuff from here, T0, here's T1, T2, T3, T4, T5, T6, T7, T8, T9, T10, T11, T12, T13, T14. Right, so we have all of these t values going from A to B, which are going to split our full interval into these individual sub-intervals. If anybody has any questions, by the way, feel free to stop me at any time. Right, and then the tagged part comes in when we talk about these values, xi sub k, which are going to be the intervals, the sub-intervals from t sub k to t sub k plus 1. So I can label any one of these a xi sub some number. In this case, this is xi sub 14. That's unfortunate. Sure, why not? Oh, shoot. Hang on. I gotta dump this out of my... Yeah. Audio needs to do that too. Yeah, sorry. That audio is going to be on the VOD, which means that it's going to... YouTube's going to yell at me. Possibly also Twitch, but we'll see how things go. Damn. Classic English biscuit, the bourbon biscuit. Has no actual bourbon in it. I know, right? Alright, so in this case, delta x sub 9 is the maximum of delta x sub k for all k in one to 14. Therefore, delta x 9 is equal to the mesh of, no, it's not quite a function, is it? Or, call it like a function. Yeah, maybe. Sure, why not? Okay. There. Okay, copy that. Delete the background. And then paste. And then we can get rid of the strays. Ugh. Right, so the Riemann sum is defined as this thing. The sum is just going to be called capital S, which uses the function f, and what's p? Yep. P is the set of tagged partitions of mesh less than some delta. Oh, hang on. Okay, the tag, no, sorry. This is a bit of what we were talking about up here, so we don't need that yet. P is just going to be a set of tag partitions. Alright, so S is just our sum. F is going to be our defined function. P is going to be our set of partitions. The function at the particular value c sub k is going to be the height of a rectangle. So however tall that rectangle is, it's going to be defined by the function itself. We saw that up here as well, right? All of our heights determined the the function values all determine the heights of these rectangles. And then here, t sub k minus 1 minus t sub k is going to be our base. Okay, c sub k is somewhere within the interval which we were talking about. So c sub 14, for instance, is just some x value within. That one might be slightly misleading. This is actually slightly higher than the actual bar coming across for the rectangle. But the general idea is that it doesn't actually matter where within that interval, the sub-interval, we're marking each of our x's. Because we're going to be taking a lot of these sums. And over a large amount of sums, especially as the sub-intervals become smaller and smaller and smaller amounts, we approximate the true value no matter what we do with our xi. So it could be something that's all the way on the left, could be something that's all the way on the right, could be anything in the middle. Yeah, I forgot to mention the other biscuit that I ate was a custard cream. Made by the same company as the bourbons. Another classic English biscuit slash cookie. Okay. So we say that f is Riemann integrable on a to b with integral I if for every epsilon greater than 0, this is the y distances, for every single epsilon that we pick, there will exist some delta, a distance in the x direction, such that the distance between the sum and the true integral, like the true integral value, will be less than epsilon for every tagged partition of mesh less than delta. So we are allowed to choose some sort of epsilon, whatever it might be. This is going to be our effectively target difference between the sum and the integral. It's also like the error, like acceptable error. Okay, so given sum right, epsilon, which is greater than 0. So your maximum allowable error cannot be 0. You can't just say like, oh, well, I'm always going to get exactly the right value. That's not okay. So pick a finite value for epsilon that is bigger than 0. Right, so given sum, maximum allowable error, epsilon, which is greater than 0, we will be able to find some sort of delta, delta, okay. Be able to find all right, so there's for every maximum allowable error that we choose, there is going to be a delta such that the difference between the current sum value, the Riemann sum, and our true integral value will be less than that epsilon for every tagged partition P of mesh less than delta. Okay, so if we have mesh less than delta, this will be for all subintervals. Okay, so what are the subintervals? Those are going to be our T, nope. then no, exactly the opposite. Um, mm. Right, so in this, we have our f of c sub k times, in this, we actually have, right, it's t sub, oops, nope, not that. That one. So yeah, if we reverse the order of our t sub k and t sub k minus 1, that's what we're going to be doing for reversing the limits of integration as well. Then, because we reverse that inside of a subtraction problem, that kicks out the negative. So it's got to be picked up somewhere. Can be picked up, yeah. Could be picked up with f, but that'd be really clumsy and awkward, especially since we need f of c sub k for doing its job with the function definition. So instead we kick the negative out front, and it becomes the negative sum of all this stuff. Then that sum now becomes an integral, again, just like how we always had it. Take the integral from b to a of f of x dx, and then we've got the spare negative sitting out. So gets gets utilized in that way, right? Make the whole rest of the expression negative. Oi. Okay, basic properties of Riemann integrals are entirely standard. Can recall them without proof. A treatment can be found in 7 or any introductory real analysis text. Well, 7. Rudin. Yep. Pretty much everybody's got Rudin. That's a good question. Do I, though? Huh. I do have a small real analysis book. I thought it was by Rudin, but maybe not. It was paperback as well. Alright, I'm not seeing it. That's alright. Okay. Integral from a to a of f of t dt is going to be equal to 0. I mean, in theory you could do that, but also if it's just going from a to a, then our b is equal to a, and so it's just going to do that. And then these are going to be equal to each other. T sub k plus 1 and t sub k are going to be equal. So that term is just always 0. We don't have to go into all that. If f is a continuous function on a to b, then f is Riemann integrable on a to b. Now let ABC alpha and beta belong to the real numbers. Let f and g be integrable functions. Riemann integrals satisfy the following properties. So it has to be linear. In other words, taking the integral of the sum of alpha f of t plus beta g of t dt is going to get us alpha times integral from a to b of f of t dt plus beta times the beta times integral from a to b of g of t dt. We also have additivity. So here, the integral from a to c of f of t dt is going to be allowed to be the integral from a to b of f of t dt plus the integral from b to c of f of t dt. Monotonicity. If f is less than or equal to g pointwise on a to b and both are integrable, then the nope, that's the next line. The integral from a to b of f of t dt is going to be less than or equal to the integral from a to b of g of t dt. Right, so if f is always lower than g, then the integral of f will always end up being lower than the integral of g. Okay. Absolute value of the integral from a to b of f of t dt is less than or equal to the integral from a to b of absolute value of f of t times dt. And for continuity in the upper limit, if f is bounded by m, the function f of x is equal to the integral from a to x of f of t dt is Lipschitz continuous on a to b with constant m. We will repeatedly need two further sequences of continuity. The first is the integral version of the mean value theorem. If f is continuous on a to b, there exists some c belonging to a to b with the integral from a to b of f of t dt is equal to f of c times b minus a. Let m be the minimum on a to b of f. And capital M is equal to max of f along the interval a to b. Okay, monotonicity gives that m times b minus a is going to be less than or equal to the integral from a to b of f of t dt, which is less than or equal to capital M times b minus a. So the average value of 1 over b minus a times the integral from a to b of f of t dt lies in little m to big M. By the intermediate value theorem, f attains this point at some value c within a to b. Okay. I think since I'm already getting kind of out of it here, we might as well go find a good raid target. I'm going to be back tomorrow at some point doing a sub-assembly required stream to put together a new bookshelf to put back there somewhere, and hopefully put some more math books on it. So I hope to see you all tomorrow. Hope you're having an awesome kind of day. And let's go over and see Casey Snow Art, who is doing some art. Character camp event. Chat picks the prompt words, then we design characters around that theme. So, sounds like an interesting concept. We'll see how it goes. Like I said, I'll be back tomorrow for a daytime, which is a little odd for me, sub-assembly required stream. We'll still do blueprints in the evening, and then on Wednesday we'll come back and do some calculation type stuff. So, hope to see you all then.